Hello everyone, so today we will do a presentation of Reinforced Concrete Design Project DCC 50203. So this is our group member.
Assalamualaikum and hi everyone. I'm Hanis Mashita and my registration number is 07DKA22F1035. So I'm going to present the design of two-way slab. This is the specification for this design of slab. Long span LY equal to 2500 mm and short span LX equal to 1800 mm. So LY divided to LX, we got 1.4, which is small than 2.0, and we got two-way slab. The materials we use for this design are: first, for the characteristic strength of concrete, we use 30 Newton per millimeter square. Second, for the characteristic strength of steel, we use 500 Newton per millimeter square. And the unit weight of reinforced concrete is 25 kilonewton per meter cube. And we assume the bar size is 8 millimeter. As you can see, this is the analysis for this two-way slab design. We got the value of short span and long span for the bending moments. And this is the main reinforcement that have been calculated, and we got the value to use for this two-way slab design. Then, this is the shear force for this two-way slab design. The design shear force, we choose the greatest value, that is 12.69 kilonewton, and after that we got the VRDC equal to 110.88, which is greater than the design shear force value, so it is okay to use. This is the deflection for this two-way slab design. Percentage of required tension reinforcement is 0.0019 and reference reinforcement ratio is 0.0055. Based on Eurocode 2 notes from the table 7.4n, the factor for structural system K equal to 1.3, and we use the formula from equation 1, and we got the value 104.64. Therefore, the allowable value is 118.2, and the actual span effective depth is 32.73, which is smaller than the allowable value. So, it is okay. The last one is cracking. Slab thickness equal to 75 mm smaller than 200 mm. For the main bar, the cracking is okay because the maximum bar spacing is 500 mm smaller than the spacing maximum for slabs. And for the secondary bar, the cracking is not okay because the maximum bar spacing is 450 mm greater than the spacing maximum for slabs.
Everyone, my name is Fatin Nur Fatiha binti Muhammad and my registration number is 07DKA22F1062, and I'm going to present about slab 1, which is two-way slab. Introduction. This presentation covers the design of a two-way slab with dimensions: long span LY 5000 mm, short span LX 3000 mm. The slab is classified as a two-way slab since LY over LX is equal to 1.67, smaller than 2. For the load calculations, permanent load with excluding self-weight, which is 4.0 kilonewton per meter square, variable load 2.5 kilonewton per meter square, self-weight of slab 3.13 kilonewton per meter square, total design load 9.63 kilonewton per meter square. The slab thickness and cover, which is we chosen the thickness, which is 125 mm, meets deflection and fire resistant requirement. For the nominal cover, 25 mm, considering durability and fire safety. For bending moment analysis, short span moment calculated using standard coefficient around 12.1 kN/m square. Long span moment calculated values around 4.13 kN per meter square. Reinforcement design, effective depth 85 mm, minimum reinforcement area 185 mm square per meter, and the selected reinforcement is main bars 10 mm diameter and the secondary bars is 8 mm diameter. For the moment calculation, first, short span and long span, we calculated moments for mid-span and support, and then for steel area requirement, we specified reinforcement bars H10 mid-moment requirement. For the shear force check, shear values for short and long spans, shear forces are calculated and they meet design limits. Next, the conclusion is design shear resistance is greater than the applied shear, so shear is okay. For the deflection check, the required tension reinforcement, we have calculated reinforcement ratio is within limits. The structural system factor, we have checked the span to depth ratio and it is acceptable. And for the conclusion, the actual span to depth ratio is within the allowable range, so deflection is okay. Lastly, for the cracking check, the slab thickness meets the requirement, so cracking is okay. For the bar spacing, both main and secondary bar spacings are within limits, so reinforcement is okay. That's it from me. Thank you very much.
Hello everyone, my name is Auji Syazwani binti Saleh, number matrix 070KA22F1050. Today, I'll be presenting my design for a continuous concrete beam. To start with the specification, we can see all the specification here, where the dimension of span L is 4.5 meter, width is 5 meter, and I use slab thickness 100 mm, and the beam size is 200 times 550 mm. Now, for the effective width and depth, calculation were performed to determine the effective flank width and beam width, which together help distribute the load effectively across the beam's cross-sectional area. So here we can see the analysis and the main reinforcement calculation. Moving to the shear force analysis, it identifies the areas of the beam that require additional reinforcement to prevent shear failure. After analyzing shear requirements, the spacing of shear reinforcement and the transverse is calculated. For deflection, I calculated the allowable span to effective depth ratio to ensure minimal deflection under load. Using table 7.4n, we found that the actual span to depth ratio of 9.02 is well within the allowable limit of 12.85. This result confirmed that the beam's depth is adequate to prevent the excessive deflection, ensuring a stable and reliable structure. For cracking, I aim to keep the maximum crack width below the limit of 0.3 mm to ensure the durability. Using table 7.1n, I calculated the steel stress and the result was 191.93 Nm square. This valuable meets the requirement for limiting cracks in the beam.
Hello everyone, today I will walk you through the process I used to analyze the beam. First, for simply supported beam, I started with the specification to understand the dimensions, material properties and load requirements for the beam. Next, I move on to the analysis where I calculated the forces acting on the beam, including bending moments and shear forces. Then, I determined the main reinforcement needed to support these forces. This involved calculating the size and spacing of the bars to ensure the beam can handle the load safely. After that, I calculated the shear reinforcement to prevent the beam from failing due to shear forces, ensuring it can handle both bending and shear stresses. With this information, I was able to calculate the deflection and cracking behavior of the beam. First, for the deflection, the calculation shows that deflection is within safe limits. This means the beam won't sag too much under load, so the structure is comfortable and stable. The outcome here is marked as OK because it meets the standards. Now, for cracking, the cracking calculation didn't pass. The reason is that the spacing between the reinforcement bars is 103 mm, but it should be 100 mm or less. With the bars too far apart, cracks could form that are larger than what's acceptable, potentially weakening the structure. So this outcome is marked as not okay. To fix this issue, we could reduce the bar spacing to 100 mm or less. Or we could also add more reinforcement bars or adjust the design, like making the beam deeper or reducing the load on it. In summary, the deflection is safe, but cracking needs adjustments to meet standards.
Assalamualaikum, nama saya Azrin Amelia Nashim, nomor matriks 07GKE22F1005. Saya akan membentangkan tentang pengelasan sama ada kolom di desain adalah slender ataupun non-slender. Saya telah mereka bentuk kolom D3 untuk spesifikasi yang telah saya senaraikan adalah ukuran untuk main beam dan second beam pada kolom. Nilai FCK dan FYK bagi kolom ini adalah FCK 30 N per mm square dan FYK 500 N per mm square. Nilai action force adalah 1050 kN. Pertama sekali adalah dimension dan size bagi kolom dan beam mengikut formula yang telah ditetapkan iaitu B darab H. Kita telah mendapatkan 2950 mm untuk LX dan 3000 mm untuk LY. Untuk beam L1 adalah 5000 dan L2 adalah 3000. Selepas itu adalah moment of inertia. Kita telah mendapatkan nilai untuk kolom iaitu 0.68 darab 10 kuasa 9 LXX dan LYY. Ini adalah kerana nilai B dan H bagi kolom adalah sama. Untuk beam pula kita mendapat 2.08 darab 10 kuasa 9 mm kuasa 4 untuk main beam dan 2.77 darab 10 kuasa 9 mm kuasa 4 untuk second beam. Selepas itu, kita akan mencari nilai stiffness bagi membahagi EI dengan panjang. Untuk kolom kita mendapat 2.31 darab 10 kuasa 5 untuk KXZ dan 2.27 darab 10 kuasa 5 untuk KXY. Dan untuk main beam kita telah mendapat 8.32 darab 10 kuasa 5 untuk kedua-duanya. Second beam 5.54 darab 10 kuasa 5 untuk KSB1 dan 9.23 darab 10 kuasa 5 untuk KSB2. Nilai stiffness ini akan digunakan untuk mencari relative column stiffness. Formulanya adalah K kolom bahagi 2 darab total K beam. Untuk Z-axis kita menggunakan nilai 0.07 untuk top end dan top bottom end, manakala Y-axis kita menggunakan nilai 0.08 untuk top end dan bottom end untuk mencari slenderness ratio. Kita perlu mencari nilai effective length of column untuk dibahagikan dengan radius of gyration. Nilai yang kita dapat mengikut formula effective length of column adalah LOZ 1667 mm dan LOY adalah 1725 mm. Selepas itu untuk radius of gyration pula nilai IX dan IY adalah sama iaitu 86.92 mm. Jadi slenderness ratio untuk Z adalah 1667 bahagi 86.92 dan kita dapat 19.18 manakala nilai untuk Y adalah 1725 bagi 86.92 dan kita dapat 19.85. Untuk pengiraan seterusnya adalah menentukan nilai untuk slenderness limit di mana rumusnya adalah 20 darab E darab B darab C dibahagikan dengan N kuasa 1/2. Untuk nilai E kita telah mendapat 0.7. Untuk nilai B adalah 1.1. Dan nilai C adalah 1.7 tolak RM, di mana rumus untuk RM adalah MO1 bahagi MO2. Untuk Z-axis RM yang kita dapat adalah negatif 0.11 dan CZ adalah 1.70 tolak negatif 0.109 sama dengan 1.81. Untuk Y-axis RM adalah negatif 0.67 dan CY adalah 1.70 tolak negatif 0.667 sama dengan 2.37. Selepas itu, kita akan mencari nilai area kolom dan FED untuk mencari nilai N. Area bagi kolom adalah 0.9 darab 10 kuasa 5 dan FED 0.85 darab dengan FCK yaitu 30 dan dibahagi dengan gamma C yaitu 1.5 dan FED sama adalah 17 N per mm square. Dan akhirnya kita telah mendapat nilai N yaitu NED bahagi SC darab FED sama dengan 0.69. Untuk Z-axis kolom adalah non-slender kerana nilai slenderness limit adalah lebih daripada nilai slenderness Z yaitu 33.56 lebih daripada 27.7. Untuk y-axis juga kolom adalah non-slender kerana nilai slenderness limit lebih daripada nilai slenderness set iaitu 43.94 lebih daripada 34.2. Akhir sekali, mencari nilai effective length of column di mana force darab dengan clear height. Faktor bagi kedua-dua x-axis dan y-axis adalah sama iaitu 0.75. Jadi LOZ adalah 0.75 darab dengan 2950 sama dengan 2213. LOY pula adalah 0.75 darab dengan 3000 sama dengan 2250. Beam untuk kedua sisi H beam adalah lebih daripada H column iaitu 500 lebih daripada 300. Setelah itu slenderness ratio bagi Z kurang daripada slenderness limit iaitu 25.46 kurang daripada 33.56 menunjukkan kolom adalah non-slender, dan slenderness ratio bagi Y juga kurang daripada slenderness limit iaitu 25.89 kurang daripada 43.94 menunjukkan kolom adalah non-slender.